In the last video, we talked about the process of evaluating an anomaly detection algorithm, and there we started to use some label data with examples that we knew were either anomalous or not anomalous, with y equals 1 or y equals 0. And so the question then arises of, if we have this label data, if we have some examples that are known to be anomalies and some that are known not to be anomalies, why don't we just use a supervised learning algorithm? So why don't we just use logistic regression or a neural network to try to learn directly from our labeled data to predict whether y equals 1 or y equals 0. In this video, I'll try to share with you some of the thinking and some guidelines for when you should probably use an anomaly detection algorithm and when it might be more fruitful to consider using a supervised learning algorithm. This slide shows what are the settings under which you should maybe use anomaly detection versus when supervised learning might be more fruitful. If you have a problem with a very small number of positive examples, and remember, examples of y equals 1 are the anomalous examples, then you might consider using an anomaly detection algorithm instead. So having 0 to 20, maybe up to 50 positive examples might be pretty typical, and usually we have such a small positive set of positive examples, we're going to save the positive examples just for the cross-validation set and the test set. And in contrast, in a typical normal anomaly detection setting, we will often have a relatively large number of negative examples of the normal examples of normal aircraft engines, and we can then use this very large number of negative examples with which to fit the model P of X. And so there's this idea that in many anomaly detection applications, you have very few positive examples and lots of negative examples, and when we're doing the process of estimating P of X, of fitting all those Gaussian parameters, we need only negative examples to do that. So if you have a lot of negative data, we can still fit P of X pretty well. In contrast, for supervised learning, more typically we would have a reasonably large number of both positive and negative examples. And so this is one way to look at your problem and decide if you should use an anomaly detection algorithm or a supervised learning algorithm. Here's another way that people often think about anomaly detection algorithms. So for anomaly detection applications, often there are many different types of anomalies. So think about aircraft engines. There are so many different ways for aircraft engines to go wrong, right? There's so many things that could go wrong that could break in an aircraft engine. And so if that's the case, and if you have a pretty small positive set of positive examples, then it can be hard for an algorithm, difficult for an algorithm, to learn from your small set of positive examples what the anomalies look like. And in particular, future anomalies may look nothing like the ones you've seen so far. So maybe in your set of positive examples, maybe you've seen 5 or 10 or 20 different ways that an aircraft engine could go wrong. But maybe tomorrow you need to detect a totally new set, a totally new type of anomaly, a totally new way for an aircraft engine to be broken that you've just never seen before. And if that's the case, then it might be more promising to just model the negative examples with this sort of a Gaussian model P of X, rather than try too hard to model the positive examples, because tomorrow's anomaly may be nothing like the ones you've seen so far. In contrast, in some other problems, you have enough positive examples for an algorithm to get a sense of what the positive examples are like. And in particular, if you think that future positive examples are likely to be similar to ones in the training set, then in that setting, it might be more reasonable to have a supervised learning algorithm that looks at a lot of positive examples, looks at a lot of negative examples, and uses that to try to distinguish between positives and negatives. So hopefully this gives you a sense of, if you have a specific problem, should you think about using an anomaly detection algorithm or a supervised learning algorithm. And the key difference really is that in anomaly detection, often we have such a small number of positive examples that it's not possible for a learning algorithm to learn that much from the positive examples. And so what we do instead is take a large set of negative examples and have it just learn a lot, learn P of X from just the negative examples of the normal aircraft engine, say, and we reserve the small number of positive examples for evaluating our algorithm to use in either the cross-validation set or the test set. And just as a side comment about this, many different types of anomalies. You know, in some earlier videos, we talked about the email spam examples. In those examples, there are actually many different types of spam email, right? The spam email that's trying to sell you things, spam email trying to steal your passwords, it's called phishing emails, and many different types of spam emails. But for the spam problem, we usually have enough examples of spam email to see, you know, most of these different types of spam email, because we have a large set of examples of spam, and that's why we usually think of spam as a supervised learning setting, even though, you know, there are many different types of spam email. And so if we look at some applications of anomaly detection versus supervised learning, we'll find that, you know, in fraud detection, if you have many different types of ways for people to try to commit fraud and a relatively small training set, a small number of fraudulent users on your website, then not use an anomaly detection algorithm. I should say, if you're a very major, you know, online retailer, and if you actually have had a lot of people try to commit fraud on your website, so if you actually have a lot of examples with y=1, then, you know, sometimes fraud detection could actually shift over to the supervised learning column. But if you haven't seen that many examples of users doing strange things on your website, then more frequently fraud detection is actually treated as an anomaly detection algorithm rather than with a supervised learning algorithm. Other examples, we talked about manufacturing already. Hopefully you've seen more normal examples and not that many anomalies. But if again, for some manufacturing processes, you know, if you're manufacturing very large volumes and if you've seen a lot of bad examples, maybe manufacturing could shift to the supervised learning column as well. But if you haven't seen that many bad examples of your own products, then I do this anomaly detection. Monitoring machines at the data center, again, similar sorts of arguments apply. Whereas email spam classification, weather prediction, and, you know, classifying cancers, if you have equal numbers of positive and negative examples, or if you have many examples of your positive and your negative examples, then we would tend to treat all of these as supervised learning problems. So hopefully that gives you a sense of what are the properties of a learning problem that would cause you to treat it as an anomaly detection problem versus a supervised learning problem. And for many of the problems that are faced by, you know, various technology companies and so on, we actually are in these settings where we have very few or sometimes zero positive training examples. Maybe just, you know, there's so many different types of anomalies, we've never seen them before. And for those sorts of problems, very often the algorithm that is used is an anomaly detection algorithm.